Welcome to Math 5200, Foundations of Geometry. The course description of this class is a rigorous study of Euclidean and non-Euclidean geometry from an axiomatic point of view, an examination of the axiomatic approach and its role in organizing mathematical knowledge. We'll also look at the history and development of non-Euclidean geometry. So in this course, we will be studying geometry from a historical perspective, and we will start with the geometry presented by Euclid, which we learned in high school. We will look at the 5 axioms or postulates that Euclid based his geometry on, and we will examine closely the 5th postulate, known as the parallel postulate. And we'll see that the development of modern geometry centers on the long controversy surrounding Euclid's 5th postulate, which is equivalent to the statement that given any line L, any point P not on L, there's exactly one line through P which is parallel to L. So this is the Euclidean parallel postulate. For over 2,000 years, it remained a mystery why Euclid's parallel postulate could not be proved. It wasn't until the 1800s when non-Euclidean geometry was discovered, and it revealed that it's an impossibility to prove Euclid's parallel postulate. So this discovery of non-Euclidean geometry had profound impacts on mathematics and science in general. It even led to new understandings of the universe with the idea of space-time continuum. Even Albert Einstein stated that without this new conception of non-Euclidean geometry, he would not have been able to develop his theory of relativity. So to study the foundations of geometry, we're going to use the following textbook: Euclidean and Non-Euclidean Geometry, Development and History, 3rd edition by Marvin J. Greenberg. Now there is a newer edition, but this edition was available in PDF form, and so I've placed this PDF copy of the textbook in our Blackboard course website. So we'll be using this textbook very closely. We'll look at material from the first 7 or 8 chapters of this book, depending on time, and we'll have homework assignments from the exercise sections of each chapter. Some other things that we need: we'll use a traditional compass and straight edge to look at some constructions in geometry using a compass and straight edge. A straight edge could be a ruler, but we're going to assume that our straight edge does not have any measurement marks. So now let's begin Module 1 on Euclid's geometry. This module will be based on Chapter 1 of our textbook. Now we'll begin with a study of Euclidean geometry, which is the kind of geometry you learned in high school, and the geometry most of us use when we look at the real world and the physical universe. It comes from the Greek mathematician Euclid, who wrote down all of the known theorems of the ancient Greeks in his Elements, which was written about 300 BC. So in Chapter 1, we'll begin with a brief history of the geometry of ancient times. So the word geometry comes from 2 Greek words, geo meaning earth and metron meaning to measure. So geometry literally means to measure the earth. Before the ancient Greeks, geometry was more of a trial and error experimental tool. We have examples of geometry in ancient Egypt, but even other ancient civilizations such as the Babylonians, the Hindus, and Chinese had certain geometric formulas. These ancient civilizations used geometry for practical purposes. The Babylonians were much more advanced than the Egyptians in arithmetic and algebra. The Babylonians knew the Pythagorean theorem, and these ancient civilizations, again, just used more trial and error and found formulas that worked for practical purposes. However, beginning with the ancient Greeks and Thales of Miletus, the ancient Greeks insisted that geometric statements should be established by deductive reasoning rather than by trial and error. So in about 600 BC, Thales of Miletus first began this idea of using deductive reasoning and proof in order to show that mathematical statements were true. So this systemization, begun by Thales, was continued over the next 2 centuries by Pythagoras and his disciples. We know the Pythagorean theorem, named after Pythagoras. The Pythagoreans were shocked to discover irrational lengths, such as the square root of 2, a number that can't be written as a fraction of integers. But square root of 2 was not thought of as a number, but it was transformed into a geometric form where they represented the square root of 2 as the diagonal of a unit square. So plane geometry was put on a systematic foundation by the Pythagoreans, and then by around the year 400 BC, Hippocrates wrote down these results in his Elements. Although Hippocrates' treatise Elements has been lost, all this material is actually contained in Euclid's Elements, which appeared about a century later. During the 4th century BC, Plato's Academy of Science and Philosophy was founded, and this idea of proving statements using logical arguments continued. Plato gives many examples of using the method of indirect proof. And then Euclid was a disciple of the Platonic school. Around 300 BC, he produced the definitive treatment of Greek geometry and number theory in his 13-volume Elements. In fact, Euclid's work has been the most widely read work in the history of mankind, and his approach to geometry dominated the teaching of the subject for over 2,000 years. The axiomatic method that Euclid used is the prototype for all what we call pure mathematics, in the sense that there's no physical experiments needed to verify statements. Only the reasoning in the demonstrations needs to be checked. Euclid also doesn't offer any practical applications of his geometry. There's a famous story that a student once asked Euclid what he would gain from learning geometry. And Euclid is said to have called a slave over and said, "Give him a coin, since he must make gain of what he learns." To this day, mathematicians still think it's noble to study mathematics for its own sake, for its intrinsic beauty. And in fact, its story goes in 2010, Grigory Perelman turned down a $1 million prize from the Clay Mathematics Institute after he solved the Poincare conjecture. Mathematicians can use trial and error and computations to inspire a result that they're looking to prove or discover new theorems, but an axiomatic method is the method for proving that a result is correct. Many times, conjectures or theorems or results are stated in mathematics without proof, or with an incomplete proof or an incorrect proof even, with only later was a correct proof given. So what is the axiomatic method? So it is a method for proving that results are correct. So if I wish to persuade you by pure reasoning that a statement is true, I could show you how this statement follows logically from other statements that you already accept. However, if you don't believe this second statement, then I have to show you a third statement and how the second statement logically follows from the third statement. I'm going to have to repeat this procedure over and over and over until we reach some statement that you accept, that I don't need to justify. So these foundational statements that we agree on as true without proof take the role of an axiom or a postulate. So there's 2 requirements that we must meet before we can agree that a proof is correct. First, we need to have acceptance of certain statements called axioms or postulates without further justification. And then secondly, a list of logic rules which tell us how and when one statement follows logically from another. Now, there's also one requirement that we took for granted. Let's call it requirement 0, which is a mutual understanding of the meaning of words and symbols used in discourse. So if there's an unfamiliar term, we have the right to demand a definition, but we need to use definitions that are subject to rules of reasoning, but we can't define every term that we use. In order to define one term, we must use other terms, and to define those terms, we must have others, and so on. But if we're not allowed to leave some terms undefined, we'll get nowhere. So when we define new words and symbols, we need to define them in terms of already defined or accepted terms that are left undefined. So here are the 5 undefined geometric terms that are the basis for defining all other geometric terms in plain Euclidean geometry. We have a point, a line, the terms lie on, as in point P lies on line AB, between, such as point C is between points A and B, and the term congruent. So when we say things like point P lies on line M, another way of saying that is M passes through P, and P is incident with M. All these have the same meaning. If a point P lies on both line M and N, we say that M and N have a point P in common, or we can say that M and N intersect or meet at P. Throughout, I'm using the word line, and in line we mean a straight line. So we'll never have to use the adjective straight to modify the word line. We always mean a straight line. So we'll just use line. There's many other mathematical terms. Since we're going to be using set notation, and the ideas of sets in mathematics is so essential, we'll be using these words set, a collection of objects called the elements. So words like belonging to or an element of a set are other terms we understand. We understand the union of two sets is the set of all the elements in one set or the other set. The intersection of two sets will be the elements that they have in common. In set language, we say that two sets are equal when they have exactly the same elements or the same members. So we can say that set S is equal to set T, but Euclid used equals in a different sense. He used equal in the sense of equal measurement, but instead of using it in this way, we're going to use the word congruent. So we would say, for example, the base angles of an isosceles triangle are congruent. So the idea of congruent means that the two objects have the same size and the same shape. Equal will be identical, so it'll be the same exact object. And then we have some common notions, such as a thing is congruent to itself, and that thing is congruent to the same thing are also congruent to each other. So these are common notions that we use in proofs of Euclidean geometry. So Euclid based his geometry on 5 fundamental assumptions called his axioms or postulates. So Euclid's first postulate states that for every point P and every point Q not equal to P, there exists a unique line L that passes through P and Q. So this postulate is sometimes informally expressed as saying that 2 points determine a unique line. And when we have a line through points P and Q, we will denote this by PQ with a line symbol above PQ. Now, before we state the second postulate, we need to make our first definition. Given 2 points A and B, the segment AB is a set whose members are the points A and B, and all the points that lie on the line AB and are between A and B. So we see the picture of the line segment AB. We call A and B the endpoints of segment AB. Now we can go on to Euclid's second postulate. For every segment AB and for every segment CD, there exists a unique point E such that B is between A and E, and the segment CD is congruent to the segment BE. So we should think of this as starting with a segment AB. We can extend segment AB by a segment BE that's congruent to a given segment. So in other words, any segment can be extended to any length. Now, in order to state the third postulate, we're going to need another definition. Here's the definition of a circle. Given 2 points, O and A, the set of all points P such that the segment OP is congruent to the segment OA is called a circle. The point O is the center of the circle, and each segment's OP is called a radius of the circle. We see that OA is congruent to itself by the common notion, so we see that A is a point on the circle, just defined. Now let's look at Euclid's third postulate. It states that for every point O and every point A not equal to O, there exists a circle with center O and radius OA. So we're using set notation throughout this chapter to discuss Euclid's postulates. So it's not really necessary to assume this postulate given set theory. We could just say that the set of all points P with OP congruent to OA exists, but Euclid had in mind drawing a circle. And so this postulate tells you that you can draw any circle with a given point O as a center and passing through another point A not equal to O. Our next definition is a definition of a ray. The ray AB is the following set of points lying on line AB. Those points that belong to the segment AB and all points C on line AB such that B is between A and C. The ray AB is said to emanate from the vertex A and to be part of line AB. So we'll need this definition of a ray and this next definition of opposite rays in order to define angles. So this definition of an opposite ray, we say that rays AB and AC are opposite if they are distinct, if they emanate from the same point A, and if they are part of the same line. So line AB is equal to the line AC. Now we can define an angle. An angle with vertex A is a point A together with two non-opposite rays, AB and AC, called the sides of the angle, emanating from A. So some important things we have that we need distinct rays, so you can't have the same ray, and we have to be non-opposite rays. So we can't have a straight line defining an angle. When we write the notation for angles, we could write angle A, or in this case angle BAC, or angle CAB. These are all equivalent ways to write the name of this angle. Here's a couple of questions to think about this definition. As I pointed out, those two words distinct and non-opposite. So think about a zero angle. Is this allowed by the previous definition? And also, is a straight angle allowed in the previous definition? Well, since the two rays have to be distinct, we can't have a zero angle, and since we can't have opposite rays, then we can't have straight angles. So the answer is nope. Neither of these types of angles is allowed by our definition of an angle. Next, we define supplementary angles. If two angles BAD and CAD have a common side AD, ray AD, and the other two sides, ray AB and ray AC, form opposite rays, then the angles are supplements of each other, or we call them supplementary angles. With the definition of supplementary angles, we can now define right angles. An angle BAD is a right angle if it has a supplementary angle to which it is congruent. So we see that we've successfully defined a right angle without referring to degrees. Now we can state Euclid's fourth postulate. All right angles are congruent to each other. So this postulate tells us that even though two right angles may be very far away from each other, they nevertheless have the same size. They're congruent. Before we get to Euclid's fifth postulate, the Euclidean parallel postulate, we need to first define parallel lines. Our author of our textbook says that this is the most important definition of the book. Two lines, L and M, are parallel if they do not intersect, that is, if no point lies in both of them. If lines L and M are parallel lines, we write this notation, L with two parallel lines and then M. So now let's state the infamous parallel postulate. So this is Euclid's fifth postulate, and it's not really the way that Euclid wrote the postulate. This is a modern formulation that's equivalent to Euclid's parallel postulate. It states that for every line L and for every point P that does not lie on L, there exists a unique line M through P that is parallel to L. And here's the picture of two parallel lines. So Euclid calls this a postulate, or a statement that is supposedly foundationally obviously true. So why should this postulate be so controversial? Well, there's a difference between this postulate and the other four. The first two postulates are abstractions of our experiences drawn with a straight edge. The third postulate derives from our experiences drawn with a compass. And the fourth postulate is perhaps less obvious as an abstraction, but it derives from our experiences measuring angles with a protractor, for example. The fifth postulate is different because we can't verify empirically whether two lines meet. Since we can only draw a finite length, finite segments, not lines, we could extend segments further and further, but we can't go on extending forever. So many mathematicians tried to prove that this parallel postulate could be proven using the first four postulates. This led to many controversies. And before we get to that, let's look at a list of all five of Euclid's postulates. So here are the five postulates in the modern formulation. For the fifth parallel postulate, we have to try to verify parallelism indirectly using some kind of proof. Euclid actually suggested drawing a transversal, which is a line that intersects lines L and M at distinct points, and then measuring the number of the degrees and the interior angles, let's call them alpha and beta, on one side of the transversal. And Euclid predicted that if the sum of these angles is less than 180 degrees, then the lines should meet and therefore not be parallel. The problem is that this criterion for parallelism is actually logically equivalent to the Euclidean parallel postulate that was just stated. So we can't use this criterion to prove parallelism because it's equivalent to the statement itself. So remember that axioms are supposed to be simple and intuitive statements that we believe to be true, that are clearly true without proof. But from the beginning, the parallel postulate was attacked as being not worthy of being called an unproved assumption. So for 2,000 years, mathematicians tried to derive the Euclidean parallel postulate from the first four postulates, or to find some other self-evident statement that we could use to replace it. But it turns out that all these so-called proofs entailed hidden assumptions that were unjustifiable, and substitute postulates turned out to be logically equivalent to the parallel postulate, so we gained nothing by substituting it. One mathematician who spent much of his life trying to prove the parallel postulate was Adrien-Marie Legendre. He actually spent 29 years trying to prove the parallel postulate and published proof after proof, attempt after attempt to prove the parallel postulate, but it turns out that none of his proofs were actually correct. And it wasn't until the invention of non-Euclidean geometry that demonstrated that no such proof was possible. Our author goes into more detail about one of Legendre's attempts to prove the parallel postulate. But there's a lot of work to be done before we can detect the flaw in Legendre's proof, So in the next few modules, we'll do all the legwork so we can confidently decide whether or not Legendre's proposed proof is valid.